Hey everyone. So this week we're going to cover the concepts of force and how they relate to and were explained by Newton's three laws of motion. So let's begin by defining force. So first thing you should know is that force is a vector quantity. So remember, vector quantities are those that have both a magnitude and a direction, right? So force is a vector quantity that is defined as a push or a pull on an object. Now, if a force is applied to an object, then the object will accelerate in the same direction, right, as the force. So it's kind of intuitive. And really, to fully describe the force acting upon an object, you must describe both the magnitude, right, the strength of it, but also the direction, in what direction this force is accelerating the object. Now, this is important because, again, we've talked about acceleration, but we haven't talked about what causes acceleration, right? And this explains to us that all acceleration is caused by forces acting on a body. So we talked about, cars accelerating. We talked about, people running. These are all caused by forces. Now, conversely, if a body or an object does not accelerate, what that means is one of two things. Either there's a zero amount of force on it, or the forces acting on it cancel each other out, right? Or add up to zero, even if there are several forces. So this basically tells us that there's two kinds of forces. We call them balanced and unbalanced forces. So to explain this, I have two images of a tug of war, right? And the first one, if you look at the one up here, we have an equal amount of children pulling on a rope, right, playing tug of war, and both teams have equal amount of strength. So we'll talk about this, but force is measured in something called newtons, and I'll explain what that means. But just know that, again, we have 200 newtons of force in the left direction and 200 newtons of force on the right direction. So what's going to happen to this rope? It's going to go nowhere, right? So that is, again, a balanced force. Even though there's zero acceleration, right, there's no movement of the rope, there are forces on it. They're just equal and opposite in direction. Now, conversely, we have a second tug of war in which the teams are not equally matched, right? We have the right team, the green team, that pull with a force of 2,500, and the blue team on the left that only pulls with 2,200 newtons of force. So in this case, we'll have an unbalanced force which will cause the rope to move in, the direction of the green team, correct? Because they have more force, so this rope will move to the right. So this will come in handy in a few slides. So, and again, force is a very, I think, both complex but at the same time pretty intuitive concept, right? If you ever played golf or seen anybody play golf, you know that the goal is to get a little white ball into a hole in the ground, and people playing golf understand that in order to do this in the least amount of hits, you use different drivers, right? Different clubs, and these clubs are made such that, again, the amount of force on the ball are different, right? You have something called a driver with a very thick head, in order to get large distances, right, on the ball, and then you have little clubs like putters, right, that allow you to hit the ball more accurately, right? So you don't use that for distance, right? You use that more for short distance but more accurate shots. So again, all this relates to the amount of force on an object, the amount of acceleration, right, that we want the object, and then eventually the amount of distance, right, that it's going to cover. So anyways, let's get into Newton's three laws of motion. So again, these were described by English mathematician Sir Isaac Newton, who again presented these three principles in a book called, most people just call it the Principia book. And it was a sort of a landmark paper that, again, even to this day is recognized as fundamental laws of motion. So much that, again, we still teach it in high school and college. So again, you don't have to know anything about the book, but I just decided to put it in here. So again, these laws describe the connection between the forces that act on an object and then the manner in which the object moves. So then this, in fact, allows to measure and predict motion of most large objects, either on Earth or even near Earth's gravitational pull. Remember, again, this was in the 1600s, so it wasn't like we were talking about space travel just yet, but believe it or not, we do use these laws in order to, to help us, to help NASA, I guess, do space travel. Okay, well, let's go into Newton's first law. Now, it's important for you guys to know that the first law is called the law of inertia. So this one actually has a name of its own. It's called the law of inertia. And what the law of inertia states is that an object in motion tends to stay in motion, and an object at rest tends to stay at rest, unless the object is acted upon by an outside force. So meaning an object that is not moving, right, will not move until the force acts on it, right? And again, I think that's intuitive. And an object that is moving, right, which I think that maybe is more complicated, right? If an object that is moving will continue to move, and in fact, it won't change its velocity, right? It should go at the same rate. So it will not change in velocity or even direction unless a force acts on it. So again, there's sort of two parts to this statement. One that predicts the behavior of stationary objects, and the other that predicts the behavior of moving objects. So again, if forces are balanced, then either the object, and the object it's at rest, it will continue to be at rest. Or you can have forces that are balanced, but in an unequal, right, amount of force, then that's going to create a motion. However, as long as these forces are still balanced, the object will maintain that motion, again, at the same speed. This again, there's no acceleration, there's just a movement, right? There continues to be a motion. And again, it stays in that motion unless, again, the forces become unbalanced. So think of a soccer ball, right? If we kick a ball, this law states that this ball will continue in the same direction and at the same speed, really forever, right? That's what it says. Now, obviously, if I kick a ball, right, and if I'm on a soccer field, I kick a ball, the ball doesn't go on forever, right? It eventually, even if nobody else touches it, it eventually will slow and stop, correct? Now, just because you don't see an outside force doesn't mean there isn't an outside force. We know that there are other forces other than, say, other soccer players on the field, right? There's something like gravity, right? Gravity will pull the ball down towards the earth and eventually slow it down. And even more important, if the ball's rolling down a field of grass, the blades of grass cause something called friction, right? And this friction will, when it's applied to the surface of the ball, will slow it down. So again, this is sort of a concept that in order to test, you would have to go into something that's zero gravity, where there's zero amount of friction or any of those forces that, again, aren't normally seen. However, they could still be measured, and we know they're there. And we think about, when Sir Isaac Newton proved this, back when gravity wasn't really fully understood, or friction, right? He described what would happen. He would describe these outside forces. And again, to you and me, it makes perfect sense because we've been hearing about this and learning about this, right? Our entire lives, really. However, when you think about that he described and mathematically proved this before these concepts were established, it really makes it even more, all the more impressive, okay? So again, with this law of inertia, we often use the word bodies or objects, right? And again, if you look at this graphic, I ask, what are the bodies, right? What are the objects in this graphic? And as we can see, there's really two objects in motion here. Even though they're in the beginning they're together, we see that it's actually a test tube person riding a skateboard, right? So that's important to understand, right? If you look at why did the test tube move forward after the skateboard stopped, it's because they're not attached. So they're actually two bodies, right? If you're driving home, you're not one object, even though you're moving together with the car. You're technically two bodies, right? And it's the whole reason why we wear seat belts, right? To keep your body on the car. And if God forbid there was any reason why your car had to suddenly stop, correct? Your inertia would push you forward. And again, if you've had the terrible luck of ever either being in an accident or just having to slam on your brake, you feel that inertia, right? Your body, if you're driving 20 miles an hour and you suddenly brake, your body still wants to move 20 miles an hour forward, right? And it's thanks to, again, your seatbelt that you don't fly out of the car. Now, again, the second question is, what is the outside force in this graphic, right? So we have what I believe is a rock in the center of the image. If this rock wasn't there, this skateboard guy would just keep going unless the friction slowed it down, the friction from the ground. But if this was a frictionless, environment, he would continue in the same direction, the same speed forever, correct? However, there is an outside force. The outside force is what stopped the skateboard. And so, again, because of the inertia, because these two objects or bodies were moving forward at a certain speed, then what happens to the skater? The skater is not attached to the skateboard, and therefore his inertia propels him forward, correct? Now, again, according to Newton's laws, he should really keep going in the forward direction at the same speed forever. But again, like I said earlier, there are other forces, correct? Namely gravity, right? So, which is the reason why he just doesn't fly or continue moving forward forever. He eventually falls. So that's another outside force. So as his inertia continues to propel him forward, the force of gravity pulls him downwards, right? And that's what causes the fall. So again, inertia is kind of the key word, and inertia is tied into mass. So what is inertia? Inertia, in scientific terms, and again, I think this is important for you to understand or to know, is the resistance of an object to change a state of motion. So it's the natural tendency of objects to resist change when they are moving, right? When they're in their state of motion. Now, the amount of inertia an object has, again, is tied into the amount of mass that this object has. Mass is a measure of, of atoms per square inch, right? We use it interchangeably with weight, right? Here on Earth, because again, we're measuring mass almost as an amount of force on the Earth. So something that is heavier has more mass, right? And so we could almost think of it as weight. So again, this is the factor that affects the amount of inertia of an object. And simply put, right, the more mass, the more inertia. Okay, so let's prove that with a thought experiment, right? So imagine that you want to stop a rock that's rolling down a hill, right? If you're tasked to stop two rocks, right, that are rolling down the hill, and you have the one on the left is a rock that has a mass of 1 kilogram, right, 1,000 grams. So it's not a terribly big rock. But on the other side, the other hill has a rock that's 10 times that size. Actually, 100 times that size. It's 100 kilograms in mass, right? So 100 times bigger. And so, again, according to the law of inertia, we know that both objects will resist change. However, they're resisting change at a different rate, right? That's not equal. It's not like acceleration of gravity where both objects fall at the same rate, right, regardless of their weight. In this case, the heavier the object, right, the more mass, the more it wants to resist change. And we know that Because if you were to have to stop a 100 kilogram rock from rolling down a hill, it's going to require more force, correct? I mean, you may not be able to do it if it picks up enough speed, right? Whereas, say, a smaller rock, you should be able to stop it easily. So again, intuitively we understand that a heavier object requires more force to stop, more strength to stop, right? Or it's going to do more damage than a smaller weight because it's going to pick up more speed. It's going to then have more inertia with it, right? It's going to resist the change in speed, right? The deceleration or the outside force. It's going to, it's going to require more force. So again, that's the concept, or the first law, the law of inertia. Newton's second law is the concept of force. So this kind of explains specifically why that happens, why object A, right, the smaller rock, requires more force than object B. So again, simply put, if I talk about Newton's second law, you should know that I'm talking about the concept of force. And what this law says is that, or it states that acceleration of an object depends upon two variables. One, the net force, right, the amount of force acting on the object, and also the mass of the object. Okay, so this means that the force acting upon an object, as the force, right, acting on an object is increased, the acceleration of the object is also increased. And as the mass of an object is increased, then the acceleration of the object is decreased, right? So the amount of force directly relates to the amount of acceleration, and the amount of mass inversely, right, affects acceleration. So again, going back to thought experiment with two objects, right? You're playing baseball, or you're a pitcher in a baseball game, and your first pitch is thrown with a baseball, which is again not much bigger than a grapefruit, right? And you throw that ball with all your strength, okay, to the catcher, and they clock that ball at 100 miles an hour, right? You're an amazing pitcher. You threw that baseball at 100 miles an hour. That was its acceleration, because you pushed it and threw it with all your force, okay, whatever that is. Now, let's say for the second pitch, they switch balls from a baseball to a bowling ball, okay? And you're tasked to throw this bowling ball to a catcher, right? So you've increased the mass, and therefore there's no possible way, even using all your strength, right, that you can throw a bowling ball at 100 miles an hour, correct? Because the amount of mass inversely affects the acceleration. So again, the heavier the object, the less the acceleration, right? Given equal amounts of force. So again, this is what the law of concept of force states, right? This is kind of a quote from the book. What it tells us is that the acceleration produced by these forces are, again, directly proportional and in the same direction as the force, right? Again, the more force, the more acceleration. So that's directly proportional. But they're also inversely proportional to the mass of the body. So again, the heavier the mass, the less the acceleration, correct? So inversely, the greater the mass, the greater the force needed to stop the object. So, when we go back to those two rocks, we know that the more mass, the more force needed to either accelerate or decelerate the object. Again, we all understand this law, right? I think it's pretty intuitive that, again, with the baseball and the bowling ball thought experiment, right? We know that heavier objects require more force to move the same distance as lighter objects. But again, what Newton's second law did is actually explain it in mathematical terms, where we can actually measure how much force is required to get a certain acceleration from an object, or how much acceleration we're going to get from an object when you input the amount of force you're going to use, right? So we can, again, predict what's going to happen to an object using this equation. So again, what we're solving for here is force, correct? And we know that force is a push or a pull on an object, right? We talked about that in the first slide. Mathematically, the symbol is F, so it's easy to remember, right? You guys all have to memorize this. So the symbol is F, F for force. And the units are important here. So units, in the short version of it, are called newtons. So we often just say, you need 200 newtons of force to get this amount of acceleration from this object, okay? But what's important to understand is that 1 newton is equal to 1 kilogram times meters per second square, okay? So it sounds weird, right? Because it's a unit that has both a weight or mass unit and an acceleration, right? We know meters per second square is a unit of acceleration. It's not a unit of speed, it's a unit of acceleration. And when we look at the equation, it makes sense why we have these units. And that is because force is equal to the mass, right, of the object times the acceleration of the object. All right? And again, mass, kilograms, acceleration, meters per second square. So again, it's going to be important for you guys to know, not just know that the units are newtons, but what a newton actually stands for. Okay? And again, the big hint is in the variables in the equation. We have a mass and an acceleration. So there's no such thing as a universal unit for mass and acceleration, right? We have to use the individual ones of both mass and the individual one of acceleration. So let's do an example. This is, again, make them as easy as possible so that you can understand the concept itself. All right? Again, my goal is not that you can do math. My goal is that you understand the concepts that these math or these equations are explaining and proving. All right? So for example 1, imagine you have a game in which you have to push or pull a rock off a table, right? And the rocks are 2 different sizes. Rock 1 is twice as big as rock 2, right? It has twice the amount of mass as rock 2. And again, the goal of the game is to obtain the same acceleration, right? So we have to accelerate these rocks. And again, let's just say you have to accelerate them to an acceleration of 2 meters per second square. That is the goal. Once you get that acceleration, you win, right? So the question is, how much force will each rock need in order to obtain this? And again, before Billy and Donnie start playing, we can calculate the amount of force that is going to be required from each player to pull their rock and accelerate at 2 meters per second. So again, I'm going to do it individually for each rock, right? And we know that for both rocks, all right, we're given the mass, right? And again, just to make it simple, I said rock 1 is twice as big, so I chose 2 kilograms, okay, as the weight. And rock 2 is 1 kilogram because, again, it's only half the amount of weight, right? So these numbers are arbitrary, and I just picked them. And okay, you'd have to be given that information. We also know that the equation is force equals mass times acceleration. Again, every time I give you an equation, your job is to try to memorize it, right? And put it in this equation bank in your mind so that you can solve for problems. So again, at this point, you memorize the equation. We're going to use the equation for force, right? Because that's what it's asking for, force. And we need both the variables of mass, which I just gave to you, and acceleration. And like I said earlier, the acceleration in order to win has to be 2 meters per second square. So for rock 1, we just simply multiply 2 kilograms, the mass, and we multiply it times the acceleration, which is, I said, 2 meters per second square. So again, what happens is I don't want to simply multiply numbers, right? I want to keep the units, like I said, last week and the week before. Always keep the units when you write these equations down and you're actually computing them. So we have 2 kilograms times 2 meters per second square. And again, 2 times 2 is easy, it's 4. But again, kilograms and meters per second square do not do not cancel each other out, do not combine, they don't divide into each other, right? You cannot make it any shorter or any simpler than that. Therefore, I keep both units. So my answer is going to be 4 kilograms times meters per second squared, right? Which, like I said earlier, equals to what? 4 newtons, all right? But I want you to not just use the word newtons. I want you to understand what a newton means. Because, again, it's intuitively when you actually write out the math, right? You can't get rid of kilograms if you're dividing by or multiplying by meters per second squared. They both have to stay. So my answer is not just 4, because that would be incorrect, correct? The answer is 4 kilograms times meters per second squared. So again, that's rock 1. That's the amount of force required for this one. Now rock 2, we're going to use the same equation and the same acceleration, so that stays. However, the mass changes. Again, we're told that rock 2 is the smaller one and only weighs 1 kilogram, right? So that's its mass. And so then we multiply 1 times 2, it gives us 2. Gives us 2 kilograms per times meters per second squared. So again, the math sort of proves what I told you earlier. The heavier an object, the more force required. And not only is it just more, but it's actually directly related. If you have an object that's twice as heavy, it's going to require twice as much force, right? So it's directly proportional. Again, that's why I use this very simple example, right? The numbers don't have to be complicated. The acceleration is proportional to the amount of force, but it's also inversely proportional to the mass of the body or of the object, which means that the heavier the object, the more force is going to be needed. And again, like I just proved, objects that are twice as heavy, right, that have twice as much mass, need twice as much force to get to a certain acceleration. All right, so what happens if instead of changing the mass, right, we change the amount of force? What happens to acceleration? Okay, so again, Newton's second law states that for a given mass, right, the acceleration produced is proportional to the force used. So let's think about this concept and use it, use an example, right, to show that. So let's say you have, again, 2 identical hockey pucks, right, that are hit by 2 players. Player 1 on the left hits this puck with 20 newtons of force. Okay, so 20 kilograms times meters per second squared of force. Player 2 uses 40 newtons of force to hit his, right? And now what I want, you're giving the force itself. Now what I want you to do is calculate the acceleration. I want to see what this change in force is going to do to the acceleration of each puck. All right, so again, the variables we're giving are going to be mass, and again, because they're equal and they're the same object, really, they have equal mass, right? So they're each 1 kilogram. So I'm giving you that. And then the other variable we're given is the amount of force used, right? I said the player 1 uses 20 newtons of force. Player 2 uses 40 newtons of force, right? Double the amount of force. So let's see what happens to the acceleration. So again, we have one equation that you have to memorize, but from this equation, you should be able to answer or formulate. Sorry about that. You should be able to formulate for any of these variables using algebra, right? That's why we covered algebra the first week. So if you don't know how to solve for A using this original equation, I suggest that you see someone at the tutoring center or review those slides on how to do that, right? So this equation is converted to A, acceleration, equals the force divided by the mass. Okay, so again, I've turned this equation into this equation so I can solve for A. I've isolated A on one side, and I get force divided by mass. So that's my equation. Again, that's something that you should be able to do on your own. And once I have the equation, I think plugging in the numbers is really the easier thing. So we know force is 20 newtons, but again, it's not good enough to just write 20 newtons, right? We have to understand that 20 newtons means that there's 20 kilograms times meters per second square, and we know that the mass is 1 kilogram, and by writing it out, I can see that I have a kilogram on the numerator and a kilogram on the denominator, which means what? these units will cancel each other out, right? Because a kilogram divided by a kilogram is 1. So we know that the number, it's going to be easy, right? 20 divided by 1 is 20. The kilograms have canceled out, so my answer is left as 20 meters per second square, which is great, right? Because meters per second square is the unit of acceleration. So the math works out. We know that I'm doing something right because I got my answer in the units that I wanted. So again, this means that if you hit a 1 kilogram puck with 20 newtons of force, you get an acceleration of 20 meters per second square. Okay. Now for the second hockey player, we changed again the amount of force because we know he hit it with 40 newtons of force, and 40 divided by 1 is 40, right? So 40 meters per second square is my answer. So again, this shows to me that if you use more force, you're going to get more acceleration, right? As long as the mass is the same, you hit a puck with twice as much force, you're going to get twice as much acceleration, right? That's intuitive. We're just, proving it mathematically. And again, not only are we proving it mathematically, but we can tell you exactly what the acceleration will be. Again, so this is to illustrate sort of the first half of that statement, right? That said acceleration produced by forces acting on the body are directly proportional and in the same direction as the force, right? More force, more acceleration. That's what we call proportionate, all right, or directly proportionate. So now that we understand these concepts, let's build on them, right? Let's talk about some, examples that are a little more complicated, more like what you might see in a quiz. So we have Mike here who's delivering a fridge, right, that weighs 100 kilograms, and we're told that Mike is pushing the refrigerator at a rate of 1 meters per second square. So we know the mass of the object being pushed and the amount of acceleration at which is, that's being produced. So if we use Newton's second law, how much force is Mike applying? So we know the equation is force equals mass times acceleration, and now we just simply input those numbers. 100 kilograms times 1 meters per second square. Again, you don't need a calculator to know that your force is 100 kilograms times meters per second squared, or 100 newtons, right? Now again, how do you, if you wanted to do this on your own, how do you practice on this? Well, my advice would be you could use the exact same example, but change the weight, change the acceleration, and make sure you still understand this, right? I could have used 150 kilograms and an acceleration of 5.38 meters per second square, right? Use those numbers and give me force. That's how you use more sample problems. All right, let's do a different one. What is the acceleration of a soccer ball that has a mass of 5 kilograms if you kick it with a force equal to 100 newtons? So the first thing you should note is that I'm not asking for force, right? I'm asking for acceleration. And that, again, that's very common, right? Because oftentimes we know the amount of force we have or we can use, and we need to find out what the acceleration of the object will be, rather than knowing the acceleration and finding out what the force is going to be. We're sort of working backwards, right? So again, the original equation is F equals ma, gives us, again, using algebra, gives us A equals force divided by mass. Again, if you don't know how to do this, you have to go back and review algebra or memorize another equation. I guess you could do that. So again, after that is simply plugging in numbers. 100 kilograms times meters per second squared divided by 5 kilograms, which is the mass, gives us, again, plug this in the calculator, you get 20 meters per second square. Okay. Good. So hopefully that explained what I think it's a pretty straightforward equation and concept. Now Newton's third law is there isn't a name for it per se, It just simply states that to every action there is an equal and opposite reaction. So what that means is that forces always come in pairs, and they're always equal and an opposite, what we call action-reaction force pairs. All right, so for every action there's an equal and opposite reaction. So the statement means that in every interaction there are actually not just one force, but a pair of forces acting on the two interacting objects. So again, if you are pulling an object or pushing an object, there's really two objects, right? Let's go back to the refrigerator and Mike. Mike was pushing the refrigerator, but what I didn't tell you is that as Mike pushes the refrigerator is actually pushing Mike back. And not only is the refrigerator pushing Mike back, but it's pushing him with the exact same amount of force. So again, that's not as intuitive, right? But Newton's third law states that the size of the forces equals the size of the force on the second object, right? So the amount of force you push the fridge is equal to the amount of force that the fridge pushes you back. And the direction of the force is in the opposite direction, right? If I'm pushing forward a fridge, the fridge is pushing me back in the opposite direction towards me. And believe it or not, what you're learning here is rocket science, basically, or at least space rocket launching science. Think about a rocket ship, right? A rocket ship is launched straight up, and it has sort of a combustion. It basically makes a combustion at the bottom of it, right? It basically, blows fuel, right, in order to create an action. The action is to push against the ground, right? And if it wasn't for Newton's third law, that would be the end of it. There would be one action. But because there is an equal and opposite reaction, as the rocket pushes down on the Earth pushes the rocket ship in the opposite direction with equal amounts of force. So that's why we need such a large, sort of violent looking explosion, right? Or fire almost, right? This rocket ship has a lot of fuel and it pushes with a lot of force. And again, the Earth pushes in the opposite direction with equal and an equal amount of force. Now the question is, if this is true, why does the rocket move upwards but the Earth doesn't move downwards, right? Why doesn't the rocket ship actually push the Earth out of its orbit, if you will, right? Why isn't that happening? Well, the truth is that this is also tied with mass, right? And we know that one object, the Earth, is much more massive than the other, the rocket ship, right? If you compare the mass of, it's exponentially larger, right? So again, because in particular in the case of this object, the first object is being anchored to the Earth, and virtually all the acceleration is imparted on the rocket ship because it's much lighter, right? So the acceleration will only be able to be measured really on the rocket ship. The Earth's acceleration is basically almost ignored. It's so small that it's almost zero. So we can safely ignore it. So if we know this concept, then we should be able to understand or be able to answer this question, right? So if a book pushes downward on a shelf with the force of 20 newtons, right? So again, let's say you hold the book up right in your hand with 20 newtons. We know that there's a force because if you were holding it up and it's a heavy book, you're going to feel that, right? We know that gravity is the force within it, right? Using the mass to push the book down towards the Earth, right? So again, if you have a book on a shelf, it's actually pushing down on that shelf with 20 newtons of force. Now, with what force does the shelf push the book back? Because again, if it's a leveled shelf, we know it's going to hold it up. That means that there's an equal and opposite reaction. So what amount of force is is the shelf pushing back, right? And if you answer 10 newtons, you would be correct. Remember, these are equal and opposite reactions. So if I push down with 20 newtons, I'm pushed back with 20 newtons of force. And because they're balanced, right, the book is not going to move, correct? You have a book on a balanced shelf. The book is not going to move on its own. And that is, again, because these forces are equal and opposite, making them balanced forces, which, again, sort of goes back to the first law. An object at rest will remain at rest unless the forces are unbalanced, or, again, unless there's another outside force that, that creates an unbalance. Okay. So lastly, let's look at another problem. All right. Let's build on that first, fridge pushing, problem. So now we know that every action has an equal and opposite reaction, which means that when Mike pushes the refrigerator, the refrigerator pushes Mike back. So now, obviously, if I'm pushing a fridge, I'm using friction, right, to anchor my legs so that I push forward and the fridge doesn't push it back. Also, most people would put it on wheels, right, so that you can slide it almost or roll it down. But let's assume that frictional forces could be removed. Let's imagine that Mike is now pushing that fridge on an ice skating rink, right, like a very smooth ice or ice skating rink. So now we have no friction. You can't just push down on the ground and anchor yourself, right, to push forward. Or, again, let's imagine that both Mike and the fridge are on wheels. So they have much less friction. And again, neither one could use that as an anchor. Now let's calculate the acceleration of both bodies, right? Because, again, we have two bodies. And again, we're going to apply Newton's third law into the equation. Now, thankfully, we still use Newton's second law so that we can compute for acceleration, right? We want to know the acceleration for each object. So we have to do this twice now. First, the refrigerator accelerates in the forward direction because, again, Mike is applying the force on the fridge, right? So we're basically going to compute the acceleration for the fridge, which we just did earlier, right? We said it was 100 newtons divided by 100 kilograms, right? That's the weight. We get 1 meters per second square. Sorry, I forgot to put the square there. Right? That is going to be the acceleration. We know it's the force divided by the mass. So that's very simple. That's 100 or 1 meters per second square in the forward direction, right? That's how fast and what direction the fridge will accelerate. However, Mike is pushed back in the opposite direction. Now, let me go back to this. I forgot to say that I've put Mike's mass. Okay, so the mass of the fridge is 100 kilogram. The mass of Mike is 50 kilograms, right? So now we have to obtain the acceleration of Mike being pushed by the force of the fridge. Okay, so now again it's flip-flopped. The force is from the fridge and the object is Mike. So we know that the force is going to be negative, right? Because it's going to be an equal and opposite force. So using the third law, you should be able to plug this number in. It's going to be negative 100 newtons. And I use the number negative because it's going in the opposite direction. And the mass of Mike, again, that's given to you, is 50 kilograms. So now we divide 100 by 50, we get 2, or in fact, negative 2 meters per second square. That means that Mike is being pushed and accelerating 2 meters per second in the backwards direction. So now, the third thing is we sort of add up these forces. What happens when we add the acceleration of the fridge at 1 meters per second square, and then we add the acceleration of Mike, which is negative 2, right? So we have 1 plus negative 2, we get negative 1 meters per second square. So that means if you were on wheels or if you were in an ice skating rink and you're trying to push a fridge, for every 1 meters per second that you move forward, you move 2 back, which means in fact you're not going to move this fridge forward, the fridge is really going to push you back, right? Which is why, again, what people do when they move heavy objects heavier than them is to remove the friction of the object, right? But again, imagine if you had to move a heavier object without any friction. This is what would happen. No way would Mike ever get to the to the forward or the end of the rink. He would be pushed back because he's moving or accelerating faster backwards than he is accelerating the fridge forward. Okay. All right, guys. As always, please don't forget you can always post questions on the discussion boards, right? If something particularly is confusing to you about this, perhaps someone else has the similar question and I can answer it sort of all at once there, right? And everyone can look at it. So, hopefully I made it as simple and easy to understand as possible, okay? Again, there's other links to help you. There's a video that you can watch. And again, email me with any other questions, okay? Have a good week.